As I recall, yesterday, this is where we left off. A function is called continuous at x equals a if three things happen, and all three of them have to happen. If it fails any one of these three, then it's not considered continuous. So a function is continuous if f of a is defined, the limit as x approaches a of f of x is defined, and f of a equals the limit as x approaches a of f of x. And today we'll do some examples. So I'm going to make up a piecewise defined function here. F of x is the function x squared minus 4 over x minus 2 if x does not equal 2. And it has, let's say, 6 if x does equal 2. So my question is this continuous at x equals 2? And I hear a quick vote for yes. You have a 50-50 chance of being right. It's either yes or no. What would you do? Figure it out. And what do you got to figure out? Basically, you got to go through the 3 steps. All right. So, step number 1. Can I plug the number 2 into that formula?
No.
Why not? That's true, but that's irrelevant. If x equals 2, according to this rule, if x equals 2, then the y value is 6. That's what this rule says. You only use this rule when x does not equal 2. So when I give you this symbol, I mean x exactly equals 2. When x exactly equals 2, f of x is exactly equal to 6. So does f of 2 exist? Yeah, it passes step number 1. What's the limit as x approaches 2 of f of x?
4.
I hear a vote for 4. I think I agree with the answer 4. And how did you get it?
Yeah. I took the x squared minus 4 and I split it up in x minus 2x plus 2. And then I figured out there was a common section, so I ignored it. And then I said x plus 2, 2 plus 2 is good.
Yep. All right, so the limit as x approaches 2 of f of x would be the same as the limit as x approaches 2 of x squared minus 4 over x minus 2. When I'm doing the limit, how come I use the x squared minus 4 over x minus 2 rule and I don't use the 6 rule?
It's not actually 2.
That's right. This symbol means x is close to 2, but it is not equal to 2. When x is not equal to 2, that's the rule we use. And you're right, this one's pretty simple. You try to plug in 2, you get 0 over 0. It factors, it reduces. You get the limit as x approaches 2 of x minus 2 times x plus 2 over x minus 2. Those cancel out. You plug in 2 and you get 4. So it passes rule number 2. It passed rule number 1. It passed rule number 2. So is it continuous? No, why not? It fails rule number 3. Not continuous. 4 does not equal 6. It passed 2 out of the 3 rules, but didn't pass all 3.
I know it is point, just not maybe, but we use a different name.
Removable. Removable. All right, so let's see if we can get a graph of this thing. I'm not sure how well this is going to work. Well, I had trouble getting the glare off earlier when I was testing it. And I'm not quite sure how to enter that as a piecewise defined function, but we'll find out. So I guess I can enter it this way. I think I have to enter it this way for this one. I think I have to enter x squared minus 4 divided by x minus 2 if x is less than 2. And then I think I'm going to have to enter it again for x bigger than 2. Because I don't think this has a not equal to option. So x squared minus 4 divided by x minus 2. And then that one would be 6.
Could you adjust the focus a little?
I will try, yep.
Thank you.
Missing part of interval, alright. Comma, maybe? Oops. Forgot to change that last number to 2. Better? Alright, so I had to enter the function a little bit weird because I don't know of a not equal to symbol. So I had to put in what happens when x is less than 2, what happens when x is bigger than 2, what happens when x equals 6. In the picture, you can see that what's happening. Well, x squared minus 4 over x minus 2 factors and reduces to be x plus 2. So the x plus 2 is the line that you see. But there's a hole right there. Why is there a hole right there in the line? Because that's what happens when x equals 2. You can't plug x equals 2 into the x squared minus 4 over x minus 2. And then what happens is, when x equals 2, the rule says the answer is right there 6. So this is called a removable discontinuity or a point discontinuity. Because what's wrong with it? One point is wrong. We've removed one point and put it in the wrong spot. So if I wanted to make this a continuous function, how could I change it to make it continuous? Nope, it's easier than that. Change the 6 to a 4. Really, all I want to do to make it continuous is I want to make this point right here fill in the hole right there. So what y value do I have to have for that point to fill in the hole? 4. So let's see if that works. Change that to a 4. Oops. Change the wrong thing to a 4. This is a lot easier to do on a computer. But unfortunately, the computer won't capture on my document camera, so I had to use the iPad. Now we have a continuous function. So when you have a picture, if you have a graph of a function, telling if it's continuous is very easy. How do you tell if a function is continuous from the graph? True, if there's no hole in it, if there's no points missing. But more generally, we say a function is continuous if I can draw the whole thing without having to pick up my pencil. Where when we had the dot up here before, I would have to draw the line and then pick up my pencil and draw the dot. I wouldn't be able to draw it in one continuous motion. Okay? All right, let's try another example. How about g of x is, oh, I don't know, somebody give me a function they like. X squared minus 2 if x is less than 0. And how about x squared plus 3 if x is greater than or equal to 0. And I want to know, is g of x continuous at x equals 0? Well, rule number 1, can I plug 0 in? Yes, and when I plug 0 in, I get an answer of 3, because x equals 0 is down here, so I plug the 0 into the x squared plus 3, I get 3. Passes rule number 1. What's the limit as x approaches 0 of g of x? Does not exist. I agree with that answer. How come it does not exist?
Because you get two different answers from the different direction.
Correct. This is a piecewise defined function. It's split at the number 0. So what we really have to do to evaluate the limit is we need to check the left limit and we need to check the right limit. So we would look at the limit as x approaches 0 from the left of g of x. And we would say that limit is limit as x approaches 0 from the left is negative 2. Negative 2 because when x is smaller than 0, we use this rule. Plug 0 in, I get negative 2. And the limit as x approaches 0 from the right of g of x is 3. Because bigger than 0, I use this rule. The limit from the left and the limit from the right are not equal. So overall, the limit does not exist. So our answer would be not continuous at x equals 0. It failed rule number 2. It was not. The limit did not exist, therefore it's not continuous. All right, let's see what that one looks like.